Let's look at belts and chains. Belts and chains are examples of flexible mechanical elements. These space-saving devices are often replacements to gearing, shafts, and other rigid power transmission devices. These devices effectively reduce cost in most cases and most commonly found in conveying machines. These flexible machine elements absorb shock loads due to their inherent elasticity, thereby damping out vibrations and increase service life. So these flexible elements are quite durable in nature. Due to their elasticity, flexible elements should be subject to strict inspection regime and should be replaced at the first sign of failure. So let's look at few examples of these flexible mechanical elements. So we've got belts. So this is a timing belt. This is a V belt, a flat belt, and finally we have chain. Chain is used, or you can relate to use of chains on bicycles, motorcycles. Again, just looking at different types of belt: flat belt, round belt, a V belt, and finally a timing belt. One of the unique properties of a timing belt is that the slippage is minimized, so there is no slippage. So it has got a perfect velocity ratio of 1. Belts are commonly used when long center distances are in play. We need to connect two components which are at a greater distance. Excluding timing belts, belts will slip and creep, thereby altering the angular velocity ratio between the driving and the driven shaft. In order to avoid this, we use idler pulleys or belt tensioners to give you a initial tension in the belt that ensures that the belt moves smoothly around the pulleys. So there are different types of belt orientation. The first one is what we call is a non-reversing open belt. So the reason why it's called an open belt is because the belt is not crisscrossing over each other. So this is an open belt drive and non-reversing. What it means is that if the driver rotates in the clockwise direction, so does the driven pulley over here. So you've got the driver and you've got the driven. Now what happens is you can see that again you've got the slack and the tight side. So how do we determine which one is the slack and which one is the tight? Again we refer to our theory that we learnt in our brakes chapter. So what happens is if the driver is rotating clockwise, so we determine the side which is slack and tight with respect to the driver pulley. So you can see that the driver is rotating clockwise. So if we just assume that this belt is fixed at this point, so you will notice as this pulley rotates clockwise, this bend or this side of the belt is pulled, so this becomes the tight side, and naturally the other one becomes your slack side. So that's non-reversing open belt system. And we've got a reversing cross belt system. So in this one you'll see that if again this is your driver, so if the driver rotates clockwise, you'll see that the driven rotates in the counterclockwise direction. So if I had to again choose which one is the tight side and which one is the slack side on this belt, so again this is a driver, assuming we fix it over here at this point, so this is rotating clockwise, so you'll see that this belt is pulled on this side, so this becomes your tight side, and actually the other one becomes your slack side. So we've got reversing open belt drive. So what we can do is, instead of using a cross belt drive system to reverse the direction of the driver and the driven pulley, we can make use of open drive system in order to obtain a desired result of having the input or the driver and the driven pulley rotating in the opposite direction. Now let's look at some of the characteristics of a flat belt. Flat belts are generally made from urethane and also rubber impregnated fabric reinforced with steel wire or nylon cords to take tension loads. One or both surfaces have friction surface coating. They are quite in operation. Flat belts have high efficiency at high speeds, almost around 98%. They can transmit large amounts of power over long distances. Usually flat belt is solved by the roll and join once the correct length is determined. So one of the unique properties of having a flat belt is you don't need to worry about geometric restriction, in the sense that you can design a machine component and then later on calculate the length of flat belt that you require. You can always go to the hardware store and then say, okay, you want X meter of flat belt. You can buy it, you can bring it back, and you can stitch the flat belt together. Another unique property about flat belts is that if you want to increase the dimension in the widthwise or the span, that is in the span, what we can do is we can stitch two flat belts side by side to increase the width of that particular belt drive system. So in that sense, flat belt offers you a lot of flexibility when you're designing a machine component. Now what we'll do is we'll slowly build towards the analysis bit of this chapter. So let's look at a open belt analysis. So the terminologies are pretty well explained over here. R1 is the radius of the larger pulley. R2 is the radius of the smaller pulley. X is the center to center distance between these two pulleys, and L is the length of the belt. So these equations, equation 1 and 2, are only true for open belt drive. So the length, the total length of the belt that you require to connect this belt drive system between the two pulleys would be calculated using equation 1. So pi into R1 plus R2 plus 2x, x is the center to center distance between the two pulleys, plus then what we have is R1 minus R2 whole thing squared divided by x. And then what we have over here is in equation 2 we have sine alpha. This alpha is very important later on, because we'll use this alpha to calculate our rep angle, which we will use later to calculate our tension ratio. So this is only true for open belt drive. Now for cross belt drive, again these terminologies again remain the same: R1, R2, X and L. The only difference is equation 3 and 4 changes slightly. So what we have is the length of the belt that is now required is given by pi R1 plus into R1 plus R2 plus 2x plus R1 plus R2 whole thing squared divided by x, and respectively sine alpha is equals to R1 plus R2 divided by x. So these equations, equation 3 and 4, are only true when you are given a cross belt drive. Now the last thing that you will be required to do is to find the power transmitted by the belt drive system. So it's pretty much straightforward. It is the difference between the tension in the tight and the slack side. So T1 minus T2 into your velocity, and velocity is your linear velocity, and velocity is simply given by pi dn upon 60. So sometimes you might be given two pulleys and then you might need to choose which diameter you're going to use. So again, common sense prevails. The driver pulley, whatever is the diameter of the driver pulley or the driving pulley, you will use that diameter to calculate your velocity. So again, your linear velocity is pi dn upon 60. So your power is simply T1 minus T2 into your velocity, and you can put pi dn upon 60 as your formula for calculating the power. So T1 is the tension in the tight side, T2 is the tension in the slack side. You've got R1, R2, you've got V, which is your velocity of the belt, which is given in meter per second, and N is the rotational speed. So please do keep this equation in mind when you're using this formula to calculate the power transmitted by the belt. So this is the maximum power that the belt can cater for. Belts are not power producing devices, but this power is, in order to write them, that this is the amount of power that can be absorbed or can be handled by the belt drive system. Now what we have is, this equation is quite familiar to you. We use this equation when we're dealing with bend brakes. So T1 over T2 is equals to exponential mu theta. Again, E is your exponential, it's not a parameter E. Mu is your coefficient of friction, theta is the rep angle or the lap angle. Again, it has to be converted into radians. So your tension ratio T1 over T2 is equals to exponential mu theta. Just keep in mind, it's not exponential raised to the power of mu theta, but exponential mu theta. So this is something familiar that we'll be using in this chapter. So what happens is a scenario would be given to you. So you might have to calculate the tension in the tight side, tension in the slack side. You need to calculate the power. You can calculate your velocity. You can calculate your tension ratio. So these are the sort of things that we'll be dealing with in this chapter. Now what happens is, as I mentioned, in the previous equation, which is in equation 6, we have theta. So for open and cross belt, we can calculate alpha. So for open drive, sine alpha was given by this relation. Then theta is simply 180 degrees minus 2 times whatever value you got for alpha times pi over 180. You will get that value in radians. And for cross drive, this equation is true. Now what happens is, when we look at equation 7 and 8, these types of problem would be given to you when we're dealing with maybe assignments or maybe a tutorial or in-class activity. But we will be looking at something a little bit more complex when we're dealing with questions that could come or could appear in your final exam. This last point is very, very important. So what this point says is, when the pulleys are made of different material, that is when the coefficient of friction of the pulley or the angle of contact are different, then the design will always refer to the pulley for which mu theta is small. So what that means is that you might have two pulleys, pulley 1 which has, let's say, mu 1 and theta 1, and you have pulley 2 which has mu 2 and theta 2. So what generally happens is, you need to decide, and how do we choose which mu we use and which theta we use. So what we do is, we take the product of mu 1 theta 1 for pulley 1, and we take the product of mu 2 and theta 2 for pulley 2, and we see for which of these pulleys, which of the combinations of mu theta is the lowest. We'll use that combination. So it's not that you'll use mu 1 and theta 2 or you'll use mu 2 and theta 2. No, you'll use mu 1 theta 1 if the product is lower than mu 2 theta 2. For which of these two pulleys, if the product is less, we'll use that mu and that theta. So now we have an example over here. So it says that two pulleys, one pulley is 450 mm in diameter, the other one is 200 mm in diameter. The parallel shafts are 1.95 meters apart and are connected using a cross belt drive. You have to find the length of the belt that is required. So cross belt, so we'll use the cross belt equations, and it says that what power can be transmitted by the belt when the larger pulley rotates at a speed of 200 revolutions per minute. If the tension in the tight side of the belt is 1 kilonewton and the coefficient of friction between the belt and the pulley is 0.25. So the first thing is, we know that we have a cross belt drive system over here. So we have a cross belt. So the first thing is, let's look at our equations for finding the length of the belt when we have a cross belt. So you'll use this equation as it is over here. So the length of the belt is simply given by this relation. So we'll substitute all the values appropriately. So diameter of the first pulley was 450 mm. Diameter of the second pulley was 200. So converting the diameter into radius and substituting all these variables correctly, we'll get that the total length of the belt that we require is 4.98 meters. The next thing is, we can find our theta, which is the wrap angle or the lap angle. So we find sine alpha is r1 plus r2 divided by x. So sine alpha is 0.167. So let's find alpha. So sine inverse of that value, we get alpha angle is 9.59 degrees. And for cross drive system, this is how we find our theta. So 180 degrees plus 2 alpha times pi over 180. So substituting all of this, we find that our theta is 3.48 radians. Now what happens is, we know our tension ratio is T1 over T2, which is equals to exponential mu theta. So exponential, then we've got our coefficient of friction is 0.25 and lap angle is 3.48. So we get our tension ratio as T1 over T2 is 2.38. T1 was given, the maximum tension, the tight side was given as 1000, so 1000 divided by T2 is equals to this, so we get T2 of 419 newtons. And finally what we do is power is nothing but T1 minus T2 into V, so T1 minus T2 into pi d n upon 60. So tension on the tight side T1 was 1000,